An applied approach on activity coefficient and ionic strength. My name is Jimmy Liu and I will be narrating this video. Our group created this presentation because we felt that activity and ionic strength are important concepts to emphasize more in Chem 120. Let's begin with ionic strength. It is the measure of the concentration of all ions in solution. It is defined mathematically as half of the sum of each ion's concentration multiplied by the square of its charge. So, now, I'll give an example. Suppose we have a 0.01 molar solution of NaCl. The ionic strength would be the concentration of Na plus 0.01 times positive 1 squared plus the concentration of Cl minus, also 0.01 times negative 1 squared. We add them up, divide by 2, and we get an ionic strength of 0.01. By the way, ionic strength is symbolized by the Greek letter mu. Moving on to activity. It is a result of the interactions between ions and molecules and their surroundings. In mathematical terms, it is the concentration of a species times the activity coefficient, gamma. Now be careful not to confuse activity coefficient and activity. Often we know the concentration of a certain species, but not its activity coefficient. And we need its activity coefficient to multiply it by the concentration to know the activity. So how do we find the activity coefficient? Let's go to the next slide. Now, the Debye-Huckel theory applies to non-ideal solutions and relates ionic strength and activity. Before I get to the Debye-Huckel equation, I'll explain non-ideal solutions. An ideal solution is one which has all ions moving randomly among one another. Rarely, however, is this the case. Oppositely charged ions attract, while some charged ions repel, and this would create a non-ideal solution. And this is where ionic strength and activity are relevant. As you can see in the equation, the log of gamma depends on the square root of mu, alpha, which is ionic size, and the charge squared. So why do activity and ionic strength matter? As I already said before, they focus on real solutions rather than ideal ones, and they also allow us to measure a solution's deviance from ideal behavior. In other words, how far away is it from being ideal? Most of you are familiar with the equilibrium equation on the left, where all activities are 1. More accurately, however, we should express equilibrium in terms of activities, as you can see on the right, because this would allow us to measure a real solution rather than an ideal one, and how far it is away from ideal behavior. Now, keep in mind that the concentration and activities may not necessarily be always to the power of 1. They could be squared or cubed, depending on molar ratios and the certain ion. Okay, we chose problem number 2 from the second test to reinforce these concepts. So, the question states, at 25 degrees Celsius, this reaction has an equilibrium constant of 399. So our job is to find the concentration of Cl- with differing amounts of NaNO3. So we will find the concentration of Cl- when there's no NaNO3, 0.0004 moles of it, 0.004 moles, and finally 0.04 moles of NaNO3. Note that NaNO3 is an inert salt, which means that it does not affect the ions in the equilibrium. It doesn't react with them. So part A, the easy part. At equilibrium with ionic strength mu equals 0, a 250 milliliter solution of Br minus, Ag plus, and Cl minus is found to have a concentration of Br minus of 5 times 10 to the negative 5th. So determine the concentration of Cl minus. This is very simple. All we have to do is plug the numbers into the equilibrium equation. So 399 equals the concentration of Cl minus over the concentration of Br minus. And we already know that Br minus is 5 times 10 to the negative 5th. So just solve the equation and we get the concentration of Cl minus equals 0.02 molar. Simple. And now on to the harder part, B. For the solution in A, determine the concentration of Cl minus if 0.0004 moles of NaNO3 were added. Alright, first we have to find the ionic strength. We take all the concentration of each ion multiplied by its charge squared, and in the end we get 0.010425. Next, we have to plug this number in to the Debye-Huckel equation to find log of gamma. And if you look up in the table, Cl minus and Br minus both have an ion size of 300 picometers. And thus, they have the same activity coefficient. So, the gamma equals 0.8968, and both the activities of Cl minus and Br minus equals 0.8968. When we plug it into the equilibrium equation, we notice that the activities cancel each other. So we're just left with Cl minus and the concentration of Br minus 5 times 10 to the negative fifth. If we solve it, we just get the concentration of Cl minus equals 0.02 molar again. So, wait, did you see that? Since Br minus and Cl minus have the same ion size, their activity coefficients will always be the same and will always cancel each other in the equilibrium, regardless of NaNO3 concentration. It doesn't matter how much the ionic strength changes, because as long as the ion size is the same, the activity coefficient in the end will always be the same. Since they always cancel each other out, the concentration of Cl minus, it will always be 0.02 molar, even in C and D. Now, so why does this trend occur with increasing ionic strength with the joint solubility of AgCl and AgBr? Well, there wasn't really a trend. As I already said before, they have the same ion size, and thus the same activity coefficient in every case. They will always have the same activity, so there is no change in the concentration of Cl minus. Keep in mind, however, that in other cases, when ions don't have the same activities, when they're different, then the concentrations will vary. And usually with increasing ionic strength, the solubilities of salts tend to increase. So I hope you enjoyed the presentation. The end.